So we have 4 flip-flops or registers. That's what like R1, R2, R3, R4. And what we're trying to do here is to separate the sequential element from the combinational element. And I'm hoping this will also help you with the homework. If you are in R1, so we just list them R1, R2, R3, R4. You can list them in any order, but here R1, R2, R3, R4. And I take this combinational element and I put it here. So this is this dashed area. This is a combinational part. And this blue area is the sequential part. So if I am in R1, next cycle, I will go to R2. So you can see here, if you're on R1, this line here, it just goes to R2. If I'm in R2, I'm just gonna go to R3 next time. So I'm in R2 already here. You can trace this line, which you will be drawing these lines, but you can just see what's happening here. This will go to R3. If I'm in R3, next time I'm just gonna go to R4, and I'm also gonna go to this XOR. So if I'm in R3, I need to do 2 things. I need one line that will go to R4, and I need another line that will go into this XOR. And if I'm in R4, I just need one line to go to the XOR. And this XOR, if you are at the XOR stage, this output is just gonna go into R1. So this output of the XOR goes into R1. So this is a system, basically, right? I hope this is very clear to you, because this is very important. And so I have a circuit like this. And actually, let me show you, since we're here. You can still see my screen, perfect. So this is a homework problem. It's almost the same, just things are moved around a little bit. Everything that's a circle is a combinational element, and everything that's inside this rectangle is a register or a flip-flop. And all I'm asking you to do is to separate them, to take all these circles and put them in a combinational logic, and to take all these registers and put them inside this memory element. So this is a different problem, but I'm gonna do this example with you right now, and I think this will be the last thing today. So I have a combinational part, like here, for example, combinational. Let's make it nice, especially when we have fun. And we also have this sequential part. Not sequential, like just a register part. So I already know this is combinational, this is combinational, this is combinational, this is combinational. So you can put them in any order you want, but I need to put them here. So this is A, B, C, and then E. And then I have these flip-flop or register parts, which need to go here. And again, you can put them in any order, but I'll just do the obvious here and make them R1, R2, R3, R4. But so now I just moved all these components here. Now we need to connect them. So when you have an input going through A, we have an input here. This is the input to the system. So we can put like something like this. Input. This input will come out of the circuit. It can either come here, or it come out here, or it can come out here. Let's not worry about this one for now, because it goes out to the whole system. But A could go to R2, right? So we're just gonna take the output from A and go to R2. And then trace it. Okay, once we're in R2, we're gonna go to B. So the inputs are here, the outputs are here. So from R2, I'm gonna go to B. And once I'm in B, I'm gonna go to C. So that's easy. I'm already in B. I can go to C. And once I'm in C, I'm gonna go to R1. So C goes to R1. Again, the inputs are here. C goes to R1. And then R1 goes to A. So this R1 goes to A. So we're basically done with this path here. So now we can do the next one. Let me highlight it. This one. So A goes to R3. So this same A could go to R3. And then R3 goes to R4. So this R3, this is the output of R3. It will become the input to R4. Why did I go on a loop and not connect it from here? Because this is the output, this is the input. Let me label it. This is the inputs to the system, and this is the output. Here, this is the input, and this is the output. But here you can connect them however you want, but like as a system. Okay, so I need to remove this one. So again, I have this A connecting to R. So from A to R3, and then R3 goes to R4. So I'm going to take the output from R3 and go to R4. And then R4 connects to E. So I'm going to take this R4 and go to E. And then E goes to C. So E goes to C. So I'm here. And then C goes to R1. C goes to R1. I already have it. I don't need to add another line. It's already connected. And then R1 goes to A. I already have that line. R1 goes to A. So we're done. That is the system. That is the solution. In the homework, it's just different configuration, but that's what I expect you to do. And once you do this, so if you want to code this in System Verilog, it's very hard because it's all over the place. You need to take this value, oops, and then wait one clock cycle, and then do some combinational logic to it, some addition, some subtraction, some kind of logic, and then do more logic and add it to a different one that came from a different path. But this one, as you will see in that lecture, which we will continue next time, once we separate them, then we can have like an always comp, right? Because we studied this. This is a completely combinational part. So we can have an always comp block explaining this transition, and we can have an always flip-flop block that explains what happens here. That's inputs and outputs. And we're done. This, you synthesize this and you will get a circuit that does whatever is explained here. I hope this is clear to everyone. If you have any questions, this is the time to ask.